Hello and welcome, folks. Today I will be tackling a TED Ed riddle called the Human Cannonball Riddle. And I do not actually solve this using my clever mind. I actually use programming and coding to solve it because I really like that idea. And just as a heads up, I don't actually know the solution when I'm coding it, so I'll be figuring it out as I go. Let's check this one out.
They call you the human cannonball, but you're really more of a pinball person. Your act involves flying through a dozen rings of fire, bouncing through a trampoline course, and catching the trapezist in the grand finale. Your cannon has metal coils that accelerate you to the perfect speed. At least it's supposed to. Today's pre-flight test fails dramatically, and upon inspection, this is a clear act of sabotage. Someone amped the power up to the max. It's too late to abort the launch. The trapezist will plummet if you don't catch him in a few minutes, so you'd better get fixing. The cannon was invented by your eccentric mentor, and as usual, his instructions leave something to be desired. The cannon's electromagnet is powered by energy cells located in 16 chambers on 2 levels. Each level is a hollowed-out square with 3 chambers to a side. The acceleration is survivable if there are twice as many energy cells in the upper level as in the lower level. Every chamber has 1 to 3 energy cells, and each side of the cannon made of 6 chambers has 11 energy cells. Your mentor designed the cannon to use a certain number of energy cells, but when the shipment arrived, it was 3 short. So he made all of those conditions work with this reduced number, and it fired perfectly. That's the amount you'll need. Too many or too few, and you and the trapezist are doomed. How many energy cells should you use, and where?
All right, folks, so here I am in Jupyter Notebook. I am going to discuss my approach as well as the code I wish I had. I think my approach is going to be to just generate all possible cannon states and then create a kind of rule set that adheres to the restrictions of the problem. Then I'm going to just iterate over all possible cannon states, apply the rule, and whatever passes will be a solution, a possible solution, and then we can analyze those solutions afterwards. So here's the code I wish I had. I think I'll make a rule set, which is just a list of rules. I think these are going to be functions that just take a single cannon state and return true or false, depending on if it passes that rule. I think I'll make a cannon generator. This is going to be efficient with memory, so that's why I like the idea of using a generator for this. But you have that, and then you have a solutions list. And then for each cannon state from the generator that you're popping out, we're going to make sure it passes each rule set. I have like little efficiency in this code here. I'll explain it a little bit later. But effectively, like each cannon state that passes the rule set will get added to our solutions list, and then we can analyze that afterwards. Okay, so this generator, I have the code here, but I think I need to explain this product function that comes from itertools in Python. So if you take the product function, and you pop in a list of like 1, 2, 3, let's see that. It kind of yields this like weird object that you can't really understand, so you have to wrap it in a list to kind of reveal what's actually going on. And we see it kind of doesn't do a whole lot. It doesn't look like anyway. It gives you like 1, 2, 3. The real power comes in when you add more arguments to this. So I'm going to add another list here of 4, 5, 6. And then you can kind of start seeing what's going on here. The product function is taking each element of one list and pairing it with each element of the second list. So you should see 1, 4, 1, 5, 1, 6, and that's what we see here. And then 2, 4, 2, 5, 2, 6, and that's what we see there. So that's what product is doing. One cool thing is if you wanted to reuse the same list, like 1, 2, 3, on top of itself, essentially, you don't need to keep adding new lists. You could just say, hey, repeat that list any number of times, right? So if I wanted it 2 times, I could do that. If I wanted it 3 times, I could do it like this. And it gives you like all the possible combinations on top of itself, essentially. So I'll be using this in my generator. The thing is, we're told that each square, each layer, effectively, has 8 positions. So instead of repeat 3, I want to say repeat 8, because I want to consider all possible states where the 1, the 2, or the 3 could be at any position within that. but that only represents like one layer. We have two, we're told. So what I would want to do is consider each layer. Let's say this is the bottom layer. The top layer is like independent. I want to consider that to also have all those combinations. So like if this is the bottom layer, the top layer could be this. It could also be this and this. So I want to actually look at the combinations of those on the layers themselves also. So what I could do is do a product of the product, which I think is a weird idea, but I would do a repeat of only two because we have two layers. So those combinations are also going to be considered. So if I run this, notice it takes a while because there's a lot of combinations going on. But here we can see like this is like one canon state. And here's a separate canon state that's a little bit different because there's a two here. So that's basically what I'm going to do for my generator. All right, so let's check out this generator. So we have this like function definition, but it uses the keyword yield. So that's how you know this is actually a generator. I have two inputs here, the number of layers, which we're told is 2 in our problem. But I like the idea of like making this more general. So I'll have that as an input, as well as the min-max range. We're told that this could be 1, 2, or 3. So that's a 1 to 3 range for each cell having that number of batteries. I believe that's what it was. Okay, so I'm going to tease out my min-max values there. And just like I did before, I have like this product in product. The inner product here is what I had before, where it's essentially like 1, 2, 3, except I want it again to keep it more general. So I have the whatever the min value is. In this case, it should be 1, but you know, it could be anything. And the max value is like 3, but the range function is not inclusive. So I need to just add 1 to give me the value, literally the value of 3. If I want to have it, it needs to be 4 for that position. Anyway, so this is going to give me essentially 1, 2, 3. That's all. And I do repeat 8 to get 1 layer. And then I do another product on top of that with a repeat of 2, but you know, whatever the number of layers is, and that will give me all those combinations, and each one will be its own canon state, and I will just yield 1 canon state every time this generator is called, and that will be the end of the generator. So, and then let's consider how this would work. So we create the generator by calling this. We pop in layers of 2, min-max range of 1 to 3, because we're told that in the problem. We will create this generator object, and then we can, I'm just going to, as an example, pull out the first 10. I'm just going to do a for loop to get the first 10 out, calling next. That's how you would pull it out on this. And so we can see this is what that would look like. If you actually look at all the possibilities, though, you will actually get 43 million possible canon states. That sounds like a lot. It kind of is a lot, but a computer can handle that no problem. I also did want to go over quickly the 3D orientation, because I'm using a flat list to represent this like 3-dimensional object. If you look at the layers, so each layer has like an index 0 through 7. This is how I would reorient that into like a 3-dimensional space. So there's going to be a north, south, west, and east face of that box, essentially. And the way I'm going to have it is the north face is going to be index 0, 1, 2. The south is 5, 6, 7. The west is 0, 3, 5. And the east is 2, 4, 7. And that's just my representation. There's nothing in the middle, we're told, so I don't need to have a value for that. And what I think is interesting is that because this is like a 3D world that we're trying to represent, I needed to keep my orientation correct. So I want you to imagine like actually physically looking at the north face of this box. If you were to do that, going left to right, you don't go 0, 1, 2, you actually go 2, 1, 0. So if you were to look at it that way, I want to create a mapping. So here I have a dictionary for each side, north, south, west, east, as well as the indices that you would need to pull out to get that representation in the order left to right. So north would be 2, 1, 0. South stays the same as 5, 6, 7. West, if you kind of look at an angle, it's 0, 3, 5. But east, you would go left to right, 7, 4, 2. And I have all those values here in my like little dictionary mapping to make life easier on myself later. All right, here I have a visualization function which takes a single canon state. Might have gone a little overboard on this, but that's okay. I won't even explain the code. I will be sharing this notebook so you'll be able to look at that. All this is going to do is represent a canon state in this very nice visual way. Okay, so here I have like the lower level colored in green, the upper level is colored in red, and the north, south, east, west is all like that. Okay, when we analyze our canon states, this is how I can represent them in a nice visual way. Okay, so I was trying to figure out how I would define a rule. I think having a function makes the most sense. A function that takes in the canon state and then spits out true or false if it passes that rule. That's it. It's not that hard. We're actually only given 2 rules. We're told that we're looking for the top layer to have twice as many energy cells as the lower level. That's just a summation thing. The second rule is where you have to take the sides into account, where each side is supposed to total 11 energy cells, including that's both upper and lower for that. So here I have a rule 1. It's a function, takes cannon state. I will tease out the lower and upper ones. I think I'll just arbitrarily pick the first layer as the lower one. All I'm doing here is summing the lower one, multiplying it by 2, and that should equal the sum of the upper layer. And that's all that rule is. It's pretty simple. Rule 2 is a little bit more complicated, but not by much. It takes in the cannon state. I'm teasing out the upper and lower levels. I have my layer mapping from before. And basically for each side of this map, so that's the north, south, east, west, all that is there, I'm going to extract the indices. So I'm just going to get basically 2, 1, 0 or 5, 6, 7, one of those. That's the indices there. I'm going to create a variable total that I will keep track of per side for each index in our indices. So again, like 2, 1, 0, I'm going to extract that from the upper layer and the lower level and add that to the total. So this will be some number that needs to be 11 essentially. If it's not 11, we can stop early and just return false. If we get through this and everything passes, then we can return true, because that means each side had a value of 11. That's that rule. And with that, we are ready to pop everything into our solution. Okay, so our solution looks not too dissimilar from what the code we wanted. We have a rule set, only 2 rules, but that's what that is. We have a cannon state generator, which has layers of 2, min-max range of 1 and 3. We'll create a solutions list, go through our generator, so it'll pop in one cannon state at a time. I have a variable called passes that I'll set to true initially, and then I'm going to just go through each rule in the rule set. If any rule is false, it will set passes to false, essentially. And if that's the case, if it is false, then we can break early, essentially. If you get through all this and passes variable is true, then we have found a solution that passes all the rule set. Then we can say, hey, that's a solution. We can add that to our list, and then we can even print, hey, we found something, and when we're done, we can print done. That's it. Let's run the code. All right, we're seeing solutions already. How quick is that? All right, so this is done. Oh, I got the word done. Okay, so it actually did finish. Let's see how many solutions we have here. We have 118. Interesting. Okay, so here's the thing. I was able to tease out these unique solutions, and here's the thing, there's a lot of duplicates in here. You have to realize that we're dealing with like this square, but if you like take the same values and like rotate them, it's essentially like the same solution. So there are actually a lot of duplicate solutions in this. I didn't consider like removing them. It doesn't really matter that much. I wanted to kind of like extract in a programmatic way each unique solution. So here's how I would do that. I'm going to create a dictionary for unique solutions. I'm going to go through each one of those solutions, tease out the lower and upper levels, and just sum both of them basically, because I need to get a total. We're told that n is like the total number of cells, so we need to find n and then also n minus 3. So that'll give us a total for each solution. If that value is not in our unique solutions, I'm going to create that as a key and set that to a new empty list. And I'm just going to add to that list, whatever it is, the solution. So I should have at least some unique keys in this. If I run that, look at my unique solutions, I see I have 27 and 30. So if I look at the number of keys, we only have 2, 27 and 30. So we basically have our n as well as our n minus 3, which is 27. So 27 is what we want to focus on because that's the kind of solution we're looking for. And if I look at 27, we see we have 4 solutions. Again, this is only because we have essentially one solution that got rotated 4 times. So if we look at just the first one of those, because it doesn't really matter which one we pick, we can visualize this. And here's a visual, and here are the observation I'm going to make. I'm noticing that the lower level has all 1s except for a 2 in a corner. So I think that's important. The upper level has all 3s in the corners and has 2s in the center except for the sides that are surrounding the 2 on the lower level. So I believe that is allowing you to kind of like eke out some efficiency, and that's why you can do n minus 3 for this one solution. So I think this is the particular orientation and arrangement that will allow us to get 27, and I think that's the answer to our problem. Let's check out the solution and see what they have.
The first step in this puzzle is to narrow the options. Let's focus on Rule 3 in isolation. We could put 11 cells in these 2 corners and fulfill it with just 22 total cells, because adjacent sides share corners. But if we put 11 in the middle chambers, we could
Wait,
have
what?
44 cells.
But you can't do
The
11.
answer must be in the range bounded by those extremes.
Okay.
We can use the other rules to refine our options further. Since there are twice as many cells in the upper level, the total cells must be a multiple of 3.
True.
Now, because of Rule 4, we need to find 2 consecutive multiples of 3 that can meet all the conditions.
Wait, hold up. Why does the solution they're explaining seem so much more complicated? It seems like I don't think I would have gone through that level of logic. Just like if I solved it on my own, I would not have gone through all that. I would have been like, that's a 3, that's a 2. Like, I don't know. It seems like so excessive. Anyway, let's keep going.
Up to this point, we haven't used the rule that each chamber must have 1 to 3 cells.
Right.
It tells us that the minimum for the lower level is 8 cells, in which case, by Rule 1, the upper level would have 16. On every side, the lower level would account for 3 of the 11 cells, so the upper would have to have 8. But if 2 opposite sides had 8, that would be the upper level's entire 16, not leaving any for these 2 chambers. So 24 is out. Let's look at the other extreme.
Okay.
The upper level can have at most 3 times 8, or 24 cells, which would give a total of 36. That eliminates 39 and 42.
Okay.
With 36, if we had 3 cells in each chamber, each side of the upper level would already have 9 of its 11 cells,
Right.
meaning we'd have to leave empty chambers on the lower level.
Because you can only
So
fit 2, right? That makes
36
sense.
is also out. What about 33? We know we don't want any sides with all 3s, so we can place 2s at opposite corners of the upper level. Now we have 8 of 11 cells per side, so we could place exactly 1 cell in each lower chamber, but that would fall short of the lower level's required 11. That leaves only 2 options, 30 and 27, which must work by process of elimination, and 27 is the one you should use. To total 9, the lower level must have 7 1s and 1 2. If you put the 2 in a middle chamber, the upper level would have too many cells.
Okay.
So the 2 has to go into a corner.
Bam, there you
and
go.
you can then place the upper level like this. You've barely snapped the last energy cell
All right,
into
hold on.
place.
Let me verify that. Okay. So the side, the corner with the 2 has to be the corner where the 1s are adjacent to it. So that makes sense. So yeah, that is the solution I found. Yay. All right.
You've barely snapped.
I think that's it. All right. I'm glad that we have a solution. I'm glad that it worked out. And I gotta say, I think I like my solution better. Maybe I'm just biased. One, my solution is generalized. So if the layers change or the min-max range changes, or even if the rule set changes. So this can handle all of that, which I definitely think is a bonus. I think I'll also say like that whole logic they went through would have taken me so much longer. I think honestly, this is like the one time I've seen where coding it took less time than like if I had figured it out myself. So that's something interesting. Anyway, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time.